bit about the dark matter problem, the evidence, the properties that we know dark matter have, the candidates. Then I will move to ultralight dark matter, discuss a bit about the theory, the phenomenology, and the problem that this kind of models have for parameter inference. And then I will finish and discuss a bit about emulators, so why it's interesting to make emulators for this type of dark matter candidate, and a bit about how to build these emulators. So, dark matter, how many of you are very familiar with dark matter? So, almost everybody, okay. So, the dark matter problem consists in the detection of gravitational potential wheels that cannot be explained by visible matter. So we look to a system, we estimate the gravitational potential based on the visible matter, we estimate based on another thing that does not depend on light, and there is a mismatch. And the phenomena that indicates the dark matter existence have very diverse spatial and temporal scales. So here I brought to you two astrophysical examples of dark matter evidence. One of them is the galaxy rotation curves that shows us how the velocity of the rotation, I can show here, how the velocity of rotation of the stars around the center of the galaxy vary with the radius. And the point is that when we look to the outer part of the galaxies, we see that the stars are moving much faster than we would expect based on how much stars and gas there is in the galaxy. So the gravitational potential there is much stronger than we would expect. So this is evidence that there is another type of matter sourcing a gravitational potential there. And in the scale of galaxy clusters, we see an analog thing, that's the galaxies are rotating around the center of the mass of the galaxy cluster, and the gas inside there is much hotter than we would expect based on the gravitational potential we would estimate based on galaxies and gas. Moving to cosmological scales, we have the power spectra of cosmology. So the power spectra are summary statistics of cosmological maps. In one side, we can have CMB maps. For example, here we have the temperature map of the CMB. So we take two different points there, and here I call it A and B. And we do this for all combinations of points, and we measure the correlation functions for these quantities. And when we make the decomposition of this correlation function in our spherical harmonics, we have this famous figure of the CMB power spectrum. And we can do an analog thing for galaxies. So we measure the correlation function of the density based on the galaxy places. It's not that straightforward, right? Because we just see galaxies, we do not see dark matter. But with a lot of mathematics and modeling, you connect this with a Fourier transform to the matter power spectra. And these spectra are important pillars of observational cosmology. Here we can see these black lines behind the observational dots. It's the fit of the standard model of cosmology, and that's the lambda CDM. And this parameterization contains a dark matter component, a cold dark matter component. And we can see that we have a remarkable agreement between the observations and this modeling. And this is very important and also a very strong evidence of dark matter. So this evidence of dark matter existence not only tells us that dark matter exists, but also gives us some hints of the properties of dark matter. So if you propose any dark matter candidate, it should obey these conditions. So we know that dark matter must be neutral under strong and electromagnetic interactions. It's almost completely because you have some models that have millicharges and this kind of stuff. We also know that the dark matter must have a limited self-interaction because we have, for example, the bullet cluster system in which we have evidence that the dark matter just pass through each other instead of heavily interacting as the electromagnetic plasma does. We also know that the dark matter must be stable with a lifetime bigger than the age of the universe because there's plenty dark matter in the universe. So if it was decaying, we would see something about it, some entropy in production or something similar. We also know that the dark matter must behave as non-relativistic matter at temperatures around keV. This is because we see galaxies that have a size that tells us that the structure formation was already happening for these time scales. And we also know the abundance of dark matter. So if you propose any dark matter candidate, it should be able to reproduce this abundance in the universe. So if you look to this list of qualities, we already know that all the standard model particles are excluded to be the dark matter. And this opens up the Pandora box of physics creativity. So people can imagine things. So we have a zoo of candidates of dark matter. Here's only a cartoon organizing based on what these candidates. So we have with a small star, that's the WIMPs. The WIMPs are maybe historically the most important dark matter candidate. It's very nice because it's a very minimal candidate. You just introduce a new particle that have a mass similar to some standard model particles between GeV and TeV. You say that this particle interacts via weak interactions. That's an interaction that we know that exists, we observe in nature. We say that it can be produced in equilibrium with the standard model particles. That's another phenomenon that you already know that happens for the standard model particles. And you reproduce the dark matter abundance. People were so impressed about this that they called this the WIMP miracle. And this is the model, the type of dark matter candidate that's excessively looked for during the past years, but we have no detection until now. But it's not completely excluded yet. And moving to bigger masses, we have the WIMPzillas that are also elementary particles, but you cannot produce it in equilibrium with the standard model anymore. We have also composite candidates as nuggets and Q balls. And the biggest masses are the primordial black holes type of candidates. And now moving to lighter candidates, we have light dark matter. This is where live candidates like dark sector, in which the dark matter does not interact directly with the standard model, but the dark matter interacts with a mediator, and this mediator interacts with the standard model. It's very studied recently. And in the end, we have ultralight dark matter. That's the topic I will discuss with you today. So to test these models, we look to the particularities of them. As I discussed before, all of them have the cold dark matter behavior in cosmological scales, but to test them, you look about their particularities, the phenomenology that distinguish them. So in the case of the ultralight matter, the behavior that we have to look for is that in big cosmological scales, it behaves as cold dark matter, but in small scales, it presents a wave behavior. But in small scales is a delicate subject for cosmologists because when you go to smaller and smaller scales, our structures in the universe become more complex and goes out of the linear or almost linear regime. So it's very difficult to model and to describe it theoretically. For example, here we have here we have the matter power spectrum, and in this end, at the same time, the data is not very precise, but we also don't know how to model this theoretically properly. So we don't know, for example, which one of these curves is the most correct to describe the end of this plot. And on top of it, we also have baryonic effects, because in small scales, the effect of stars, black holes, AGNs become important, and these are very complex phenomena that we are not able to make a good modeling of from first principles. So it's complicated to test the
It's not a modeling, it's not a fit, it's a modeling, a different curve.
Yes, it could be different modeling, or you're trying to put your physics there. But
Today depends on.
for example, if you have ultralight dark matter instead of CDM, you would have a different curve, but very hard to describe how it would be for cold dark matter or for ultralight dark matter is that it's hard to write the theoretical prediction in small scales.
Place for simulations.
Yes, you need simulation or something similar to do this. But in general, for example, for ultralight dark matter, these simulations are very expensive, so you can do just small ones. Oh, it was the wrong one. So one example of tension between the cold dark matter model and the observations is the cusp core problem that consists in a discrepancy between the simulations of in small scales for cold dark matter that predicted that inside galaxies we will have a density profile that follows Navarro-Frank-White. In this figure, it's this gray line. And here we have the observations, and we can clearly see that there's a discrepancy. And this maybe is due to the baryonic effects, but it can also be that the dark matter does not behave as cold dark matter at small scale. This is an open question. And in our case, we choose to work in maybe it's not CDM inside. So this moves us to the next topic, that's ultralight dark matter. So ultralight dark matter is a class of dark matter candidates that lives roughly in this mass range. And this mass range is so small that it implies that the de Broglie wavelength of this candidate is of astronomical size. So it's an extremely light particle that have a, you ask something? So you will have this astronomical de Broglie wavelength, and this up and down limitations comes from, in first place, we want this wave behavior to be just inside the galaxies, so we want to keep ultralight dark matter like CDM in big scales. And by other side, we want to see this wave phenomenology. So we impose an upper limit for the mass that says that the de Broglie wavelength must be bigger than the interparticle distance in order that this wave phenomena will appear. And since this is so light, to account for all the dark matter mass that we know that is present in galaxies, we need that these candidates to be bosonic, because if it's fermionic due to the Pauli exclusion principle, we cannot put all the particles inside the galaxy. And how do you study the cosmological behavior of such a candidate? So now I will focus for ultralight dark matter of spin 0. That's the simplest case, but also the most well-described and explored and tested. So for spin 0 ultralight dark matter, we just begin with the action of a scalar field. We impose that the universe is homogeneous, is isotropic, and is expanding, and you will obtain this equation of motion. And when you solve this equation of motion, you see that in the regime in which the Hubble parameter is much bigger than the mass of your particle, the field is frozen. And in the regime where the mass is much bigger than the Hubble parameter, your field will oscillate. Just to remind everybody, the Hubble parameter will go smaller and smaller when the time goes on. So for a fixed mass, probably your dark matter candidate will have during a time like this, and then we'll change its behavior to oscillatory behavior. And when you use the relation between the energy density and the field value, and during a bit more math, you find the result that in the regime where the Hubble parameter is much bigger than the mass, you have a dark matter, ultralight dark matter that behaves like dark energy with an equation of states -1. So it behaves like a negative pressure fluid. And in the regime where the mass is bigger than the Hubble parameter, you have a pressureless fluid in average, so behaving as dark matter. And when we talk about a structure formation, so go ahead.
The last property you mentioned, does it mean that in some of those models you can get rid of the cosmological constant because you get the effect of dark energy you apply that model? Yes,
exactly. There is plenty dark energy models that are based in scalar fields. And if you do like the mass is near to the Hubble parameter today, the candidate will behave just as like dark energy until today. So it's one type of dark energy candidate. May I move on? So in this non-relativistic regime, and where the mass is much bigger than the Hubble parameter, you can start forming structure with this kind of candidates. And in this regime, you can describe ultralight dark matter with a Schrödinger-Poisson system of equations. And the nice thing is that if you do a change of parameters like this, you arrive at the Madelung equations that are hydrodynamic-like equations for this fluid. And what you find that's nice is this last term that's called quantum pressure term. And it's present only in ultralight dark matter candidates, but because it's related to this very long de Broglie wavelength. And this term acts like a pressure, so it will counteract gravity, implying a suppression of the gravitational collapse. And this will imply that this kind of model will have a finite Jeans length. What means that there will be a typical scale that depends on the mass of the candidate, for which for scales smaller than this one, there will be no growth of structures. So it's a very important feature of this candidate. And in the context of galaxies, it will imply enough finite density central region for these models and enough current profile. So this kind of model solves the cusp core problem. So it's a nice motivation to study this kind of model. Beyond this, we also have that these ultralight dark matter waves trapped inside the galaxy will interfere. So they will distribute with an interference pattern inside galaxies. We can call this a granular halo in opposition of a smooth halo that formed in CDM. And the most important thing for my project now is that this suppression of structures will imprint in the matter power spectrum. Here we can see that the suppression is very dependent on the mass. So the bigger the mass of the ultralight dark matter, the smaller the scales in which the suppression will show up. And through the rich phenomenology of these models, there is already a lot of observational bounds on it. But as I explained it before, these small scales physics are complicated. People, we are not completely sure about the physics in this scale. So it seems that completely excluded to be only dark matter. But in the truth, you need to look at these bounds with a bit of salt, because we are not completely sure about this physics. And maybe in 2 or 3 years, many of them are already gone, or they are moved by 1 or 2 scales. But the best chance for us is here between 10 to the minus 19, 10 to the minus 20. Is where we have more uncertainty about our bounds. However, for these models, it's not an easy task to compare the cosmological observations and our theory predictions, because from the data side, the data is already complicated because we have a big volume of data. In the cosmological models, we have many free parameters. So to do a good and robust statistical parameter inference for this kind of model, we need Bayesian techniques like an MCMC that requires a lot of computations of the theoretical predictions, of order of millions of times of computations and comparison between your data and the theoretical predictions. Here I brought as an example a triangle plot of a Planck paper. So here we can have the idea of how many different parameters we need, but it's just a small set of all the parameters that Planck tests. And in the theory side, we have, as I said, the ultralight dark matter field will oscillate, and the oscillations are trouble because it's hard when the oscillations become fast. It's very hard to model analytically and very difficult to treat numerically. So the computations that are needed to compute the cosmological observables for these models are very difficult to do. There are people that have already build the Boltzmann softwares, Boltzmann solvers for this kind of model. We have Axiom-Cam, AxiClass, and Axie-Cam. But all of them take a time of water 1 minute to compute the predictions just for one combination of parameters. So if you think 1 minute times 1 million times, it's a lot of time. It's very expensive, expensive computationally. So the idea for our project is to overcome this problem with a Boltzmann code emulator for ultralight dark matter. So the strategy is to replace the Boltzmann codes that make these very complex computations that take a lot of time by an emulator based on neural networks. So what's an emulator? So it's a machine learning here. And the idea of an emulator is a computer program that is able to learn the dependency of your observable, in our case, for example, the matter power spectrum, in your parameters. And it does this based on examples you give to the computer. And we call these examples the training set. And in the end, it works like a multidimensional interpolator. So you give it to it many examples, and it learns the patterns of how your observables depend on the parameters. And the nice part is that once your emulator is trained, it can give you the theoretical predictions at time of other milliseconds. So it's a huge improvement in speeding up the predictions. So neural networks, you can base your emulator on many machine learning techniques, but we choose to work with neural networks that are machine learning algorithms based on layers and nodes. For one node, you have that the input is a linear combination of numbers, and the output is a function of these numbers. And you can choose different forms for this activation function, and the one that you choose depends on your specific problem. So in the truth, you need to test which one is better for your problem and your application of neural networks. And how a neural network learns. Okay, so I give it to its main examples and how the magic happens. In the end, it's a bit simple thing. To learn, what a neural network will do is to minimize the loss function here, sorry. The loss function, that is a quantitative way to look how bad is your emulation, and you need to minimize this quantity. Here I have an example of loss function that is the mean square error that compares the target function evaluating the parameter theta I and the neural network prediction of this target function. And what the neural network does is to minimize this function with respect to the W values. So also we know that the neural networks have already been used in the literature to emulate tasks of Boltzmann codes. And we have seen that it's able to achieve percent or sub-percent accuracy, what's very nice. And also it's good to deal with a large amount of data. And so to make it clear in our project, so we want to use a neural network to build an emulator that will have as input the mass of the ultralight dark matter, the fraction that says how much of dark matter is ultralight dark matter, and all the cosmological parameters. Here I put, for example, the baryon density and the Hubble parameter. And the output we want are like the cosmological power spectrum, the CMB and the matter power spectrum, and other derived parameters as omega lambda, sigma 8, and etc. Sigma 8, sorry. So to do this, we have two big blocks of work. The first one is to design our training set. So we need to choose which quantities are we emulator for which range of parameters, how big it needs to be our training set. And the other block of work is to find the ideal network, because there's no recipe to choose the architecture of your neural network. It's very, very problem dependent. So if I want to build an emulator for power spectra for a neutrino model, it will have a different idea architecture that of the ultralight dark matter. It really depends on your training set. So it's our work to test, it's by trial and error. You test different architectures and you see what's better for your case. So in our case, for generate our training set, we choose Axie eCamp, that's the most recent one, because they have very nice progress in efficiency and in precision with respect to the others. And we will not like build a neural network by our own programs, but we will use this Connect as a framework for training. It's a very nice program. They have this training part, but they also have a kind of parameter inference between built in that is like a hybrid neural network Boltzmann code algorithm, but we will use by now just the neural network part. And here's my final slide. I'm sorry if I spoke too fast, but here's a preliminary results that the things that I have emulated before. And here we can see some nice features. For example, here the curve is very well emulated, but when you move to smaller masses, here it already starts to miss some features. And here the same thing. And our hypothesis is that because we have a diverse behavior here, like the scale changes drastically with the mass, and here it could be a problem of the architecture that's not adequate. But here in the end, we know that the problem is we don't have enough data. It was just a quick test with a small training set. And when we add more data to it, it will improve.
On the other hand, you know, the one that you're missing are for sure already rolled out anyway.
Yes, yes. But the idea of the emulator, we want to make it as broad as possible to make people free to put their own priors for parameter inference. So the idea is like to have a good emulation for everything, even if it's excluded.
Just not sure I understand the last part of main illuminations. So there are several curves, like there's a dash curve which is supposed to overlap the non-dash curve in for each
Yeah.
curve.
The dashed curves are the examples I gave to the neural network, and the continuous curves are the emulated ones.
Okay, so then you want them to agree, and you're saying for small k, it starts in
For small masses.
for small masses.
Yeah, it starts to miss. For example, here, but it's not like a scale of the mass. For example, here is divided in two mass ranges. Here, oh, I should move there. Maybe. Okay, now here it works better. Here's 10 to the minus 21 to approximately 10 to the minus 26. So this is the heavier ones. And here you see that in the end of this training set, it starts to miss the feature. Here, in the other side, the smaller masses. I start in 10 to the minus 26 and go up to 10 to the minus 30. And it starts to missing the features here. So it's not like a physical thing, it's just how diverse is my training set. If I divide it in more range of mass, it becomes better. Because it's very diverse, so the neural network needs to understand more features, and for it to understand more features, I need to give it more examples.
When we can easily solve by more.
I hope so. I will figure out now we are doing like the less because we have very fine-tuned decisions. For example, we have numerical problems in the truth for very small masses. And so we need to choose what the maximum fraction we will allow for very light candidates. And we need to make like this kind of a lot of small decisions. We are in the last one to generate our final training set. That will be huge. It will be around 5, how to say this number? It's 5 times 10 to the 5. So it will be huge. And we need to like really take care of all of our decisions because it will take a lot of time to run.
This drop is just because you stop the solution, because the sudden drop there.
Yeah, I stopped because you'll see it goes down very fast. So if I keep like this curve until here, I would have just numerical waveforms, right? Because the numbers go very, very, very small. So it was a try to deal with this problem. Now we know it doesn't work very nicely because the neural network doesn't deal like with these zeros here. So the solution we have is to stop, to not allow the fraction here goes up to 1, but go to 99%. It's enough to keep this plot until here. And that's all. Thank you very much for your attention. And if you already have any other questions, I have to go.
Thanks. No, we have plenty of time. Questions, discussion. So what parameters are you emulating?
It's the fraction, the dark matter mass, the AS, like the primordial spectra, the NS, the Hubble parameter, the total amount of dark matter, and there are some missing, but I don't remember it by heart. But there are 6 cosmological parameter plus 2 of my model. Any other questions?
So just a comment that this is work that's actually, I'm just very distantly co-advising. It's mostly her with Elisa Ferreira, so just to make sure that it's mostly her work. So I'm I don't own any of the credit for
Okay.
with this. So. I actually have a question that since I'm a bit far, sometimes I don't understand fully. So if you go back to the spectra that you're looking at there, right?
This
Yeah, I mean, these oscillations, they seem to be self-similar, and it's just a rescaling. It seems like they are very much a rescaling.
This one is not like the right curve. It's an analytical approximation that I use it like since the programs take a lot of time to run. We use an analytical approximation just to study the architecture that meets this. Maybe here.
So maybe, yeah, in one of the earlier,
This one,
yes, that's what I wanted to see, yeah.
this
So-
one is like
so-
the real plot. You see, it's not that self-similar.
Right, but they are also missing, the statistic maybe isn't perfect there, right? I mean,
This
do you have a zoom in of that figure?
No, I
No.
don't think so. Let me check.
Yeah, there you go. Yeah, this
Yeah.
one, right? Yeah, it looks like the resolution isn't very good, right? So, yeah, but in any case, I see your point. It's not self-similar.
Yeah.
Well, also because you have baryons, you have everything else, which is just breaks that scalar variance.
Yeah, here is like the real computation, the other is only an analytical approximation. But yeah, it's weird. Like I put what the heck done? Maybe if I put more points, it will be more beautiful, well behaved like this, but it becomes very, very, very fast. So I don't know which kind of resolution would be enough to have a beautiful plot.
So this is on the solving the Boltzmann equation.
Yeah.
So what are the inputs for this Boltzmann equation?
It's lambda CDM and
The equation that you showed in the beginning, that these 2 sets of, I know you show some Boltzmann equation. These are bosons. What is that equation?
they start,
Is it this equation that?
yeah, they start with the Schrödinger-Poisson equation in this Boltzmann solvers, but when it starts to oscillate very, very fast, they can't do this anymore. So what they do is like to make an effective mean of the oscillations, and they evolve with evolve. Thank you. They evolve the system with this effective fluid approximation. That's like the mean of the oscillation. Yes.
And just to be sure, it's just called quantum pressure, but there's nothing quantum about this. It's fully classical, right? Just
Yes.
there's no H bar here.
Yeah, it's like it's something related to the uncertainty principle in the truth, because since the lambda de Broglie wavelength is very, very big, you cannot like localize the particle. So there will be this pressure, yes. In for-ultralight dark matter, this layer between quantum and classical is always very strange. Yeah. So any other question?
Okay, thank you. Yeah, so yeah, we can have a long coffee break.
Eu falei muito, muito rápido.
It also gives time for Ricardo to finish this.
Ah, obrigada.
Você pouco perguntou tudo.
Uhum.
Você mostrou um aspecto da matéria, uns pontos que são críticos. Para pequenos escalas, velocidades grandes, os pontos eles não estavam naquele regime não linear. Eu queria saber por que eles estavam.
Da série?
Cara, essa última semana eu estive bem ocupado fazendo slides, mas semana que vem eu vou estar mais tranquilo, daí eu tá trabalhando no negócio. Sim. Agora, principalmente agora que chegou os dados do Downpour, né? Aí, o que eu comecei a fazer foi, na real, eu comecei a baixar uns catálogos de galáxias, tipo, do Legacy Survey, para tentar fazer um catálogo próprio nosso de galáxias, um catálogos diferentes, fazer um super catálogo do céu inteiro, e aí ver se eu consigo calcular a correlação cruzada dos dados desse mapa de galáxias com os dados novos do
Mas, tipo,
mas
aí tem um overlap que a Isabela tá fazendo. Era só isso.
Não tem.
Ou não?
é que eu acho que sim, mas a Isabela tá usando Blade, né? Tá usando Blade Pro. E aí é mapa de magnitude, né? Não é redshift, né?
Você apresentou o Blade.
Aliás, não é um mapa de montagem, né? É um mapa de magnitude, não?
Não, mas
Ele não tem ele não tem um catálogo de tem.
Mas é tipo assim, ele é uma mistura, né? Então ele é bem heterogêneo. Eu não sei se isso não usou outras.
Ele era só pegar tipo, posição das galáxias.
Você conseguiu baixar aí? Pega o celular.
Oi? Eu só baixei o catálogo, assim. Só baixei, tipo, as posições. As posições e os erros nas posições. E daí agora, tipo, ver se eu consigo, eu mesmo fazer minha própria máscara, ou ver se tem a máscara já disponível lá no catálogo. É do Desi Legacy tem. Que daí é só baixar também a máscara e.
É. Qualquer coisa você fala com o Roberto, que tem tudo de máscara. Então, estava hoje, inclusive, na defesa da Natália, hoje, um dos membros suplentes, até apareceu na defesa, que é o Sérgio Comidas, que é o cara que,
Sim.
que é o cara que faz o Semana de Model. Né? E eu até falei, se não estava escrito para você faz tempo, aqui nos achei mesmo uma coisa específica.
aqui ainda tem. É porque eu
Vai acabar mais fácil chamar ele para
Sim. Eu li o paper lá.
Você leu o paper que eu
Sim.
mandei, né?
Sim.
Então, e aí tem basicamente é rodar um código, entendeu? Mas daí eu pensei também Uma outra coisa que seria mais importante do que conversar com ele é não só ter a questão de galáxias, só a possibilidade que a gente vai colocar, né? Mas também ver se tem AGNs. Se a gente consegue colocar AGNs. Porque tem toda essa história de você poder fazer ter um canal de AGNs, especialmente para as massas maiores, aquela história toda, né?
Pô, eu não sei
E
se.
eu acho que.
Desculpa.
E eu acho que alguns desses chefs também colocam galáxias e AGNs, fazem tipo o trabalho completo. Você fala.
Pô, então, não sei se viu essa semana, saiu um paper justamente com a ideia que tu tinha dado
Claro.
de usar a correlação cruzada para medir a atração. Né?
Não.
Eu esqueci o nome. Matheus. Sabe como é? Kainan, eu esqueci também.
Então, você vai bem devagarinho. Não, essas coisas você vai.
Eu achei que eu também era só. Eu também.
O pessoal é bem
Perfeito.